All right, let's dive right in. Today we are tackling a really crucial skill when you're working with rational expressions, and that is finding their domain. Now, it might sound a little technical, but trust me, it all boils down to one simple, absolutely unbreakable rule.
So I've got a question for you. What do you think it is, the single most important rule in all of algebra? I mean, this is a rule so fundamental that if you break it, the whole system of math just kinda falls apart.
And there it is. That's the one. This is our golden rule, our prime directive. Absolutely everything we're about to do is built to defend this one law. It's the foundation for our entire mission today.
And yeah, I want you to think of it just like that. You're basically a detective. Your mission, should you choose to accept it, is to hunt down those very specific numbers. We'll call them the danger zones that would force us to divide by zero. You ready to start the investigation? First, we got to know what we're looking for.
So what is this thing we're dealing with? Well, a rational expression is really just a fancy way of saying it's a fraction, but the top part and the bottom part are both polynomials. Basically, think of any fraction that's got variables like x hanging around.
And this slide breaks it down perfectly. Over on the left, you see exactly what we're talking about. Polynomials on top, polynomials on the bottom. Simple enough. But now look at the right. The top one has a square root of x, and the one below it has 2 to the power of x. Uh-oh. Those aren't polynomials, which means those expressions are not rational. So today, we're staying laser-focused on the stuff you see on the left.
Okay, every good mission needs a solid plan. So here is our simple 3-step strategy for sniffing out those dangerous x values and figuring out the domain.
This is your entire toolkit right here. Step 1, isolate. That means you are going to completely 100% ignore the numerator. Forget it even exists. Your focus is only on the denominator. Step 2, solve. You take that denominator, you set it equal to 0, and you solve for x. And finally, step 3, exclude. Whatever answers you just found, those are the numbers that x is not allowed to be. Let's see how this works in the real world.
We're going to start with a nice, straightforward example to get warmed up. This is about as basic as it gets, but it's perfect for seeing the plan in action.
So here's our function. We've got a 7 up top and an x minus 5 on the bottom. Now, remember the mission plan. What's the only part we actually care about here? You got it. Just the denominator, that x minus 5. So as you see, we take that expression and we set it equal to 0. From there, it's just a tiny bit of algebra. Add 5 to both sides, and boom, we find out that our solution is x equals 5. This is our one and only danger zone for this function.
So, what does this actually mean? It means the domain is every single number in the universe except 5. If you dare to plug in 5, you get division by 0 and the whole thing breaks. Any other number, totally fine. Okay, let's level up a bit. What happens when the denominator is a quadratic? This is where those factoring skills you've been practicing become absolutely essential.
Here's our new function. Now again, that numerator, the x plus 1, what do we do with it? We don't care about it. Our focus is locked squarely on that x squared minus 9 in the denominator.
Okay, check out how we break this down. We grab that denominator, x squared minus 9. Now, you probably recognize this guy, right? It's a classic difference of squares, and that factors out into two neat little pieces, x plus 3 and x minus 3. Now, each one of those could be a problem, so we set the first one, x plus 3, to 0, and that gives us our first danger zone, x equals negative 3. Then we do the same for the second one, x minus 3, and that gives us our second, x equals 3.
And there we have it. Our domain has two restricted values this time. X can be any real number you can think of, just as long as it is not negative 3 and it is not positive 3. We've successfully identified two danger zones.
All right, let's jump into our final field exercise. This one might look a little more intimidating, but I promise you, the mission plan, it stays exactly the same.
So here's our function. We've got a cubic polynomial down there in the denominator, x cubed minus 4x. Don't let it scare you, just trust the process.
So the very first step is always to factor, completely. We look at x cubed minus 4x, and we see they have a common factor of x. So let's pull that out first. That leaves us with x times x squared minus 4. And hey, would you look at that? Another difference of squares. So we can break that down even further. Suddenly our denominator has three separate factors, x, x plus 2, and x minus 2. Now we just set each of those to 0, and we get three distinct danger zones, 0, negative 2, and positive 2.
And that gives us our final answer. The domain is all real numbers except for -2, 0, and 2. See, the process works no matter how complicated that denominator might look at first glance.
Okay, mission accomplished on those examples. So let's have a quick debrief. Knowing the plan is one thing, but knowing how to avoid the common traps, that's just as important for success.
These are the two biggest mistakes I see people make all the time. The first trap, getting distracted by what's happening in the numerator. The truth is, the domain is only, and I mean only, about what's happening in the denominator. The second trap is not factoring all the way. If you just look at x squared minus 9 and don't break it down, you might miss one of the solutions. The truth is, you have to find every single factor to find every single danger zone.
So you might be sitting there thinking, okay, this is neat for a math class, but when am I ever going to use this in real life? Well, it turns out the stakes can be surprisingly high.
Get this. In electrical engineering, a lot of circuits are actually modeled using rational expressions, just like the ones we've been solving. And a value that makes the denominator 0 isn't just a math error on a piece of paper. It actually corresponds to a real-world physical thing called a resonance frequency. And if you hit that resonance frequency, it can cause the circuit's output to spike uncontrollably, theoretically shooting up towards infinity. So finding the domain isn't just about passing your algebra class. For an engineer, it's about preventing a catastrophic failure by identifying and avoiding those dangerous inputs from the very beginning.
Okay, so we've gotten really good at identifying the numbers that x isn't allowed to be, but that leaves us with one last really interesting question. What does a function's graph actually do when it gets close to these forbidden values? What does it look like? Well, that's a mission for another time, one that involves some cool ideas called asymptotes and holes. Thanks for tuning in.